You can also include the clear all statement. This will get you a clean workspace. Second, we are going to load two images. First image is called A image, is office2.jpg image. Second is a tired.tiff image. The tiff image is already a grayscale image, so we don't need to convert that image into grayscale, but we need to convert the A image into a grayscale image. So after we have two grayscale images, I and A, we just use the histeq function to equalize their histograms, which will in return equalize the contrast or enhance the contrast, and finally we will just plot that images. So that all for the code if you are going to do this with the help of built-in functions. But it will not allow us to learn what is going behind or how it helps us in our complex MATLAB projects. So first of all, we need to understand why the histogram equalization is important, or why the contrast enhancement is important. And also you may ask that why we need to learn the histogram and why we need to focus so much attention on histogram. So I am going to answer all of these questions, so keep patience. First of all, why we need enhanced contrast. So as you can see that the contrast is very important. A good lighting condition will always give you more information that you may retrieve from that image. In our example office image, where we have very bad lighting condition, we may end up, if we start doing processing on the without enhancing the contrast, we may end up having very few objects or no information at all when we convert it to a binary image or some other processing on that image. Because the main goal of the computer vision is to retrieve an information from that image. Although in the image processing is the first building block or the first step to the ladder to the computer vision. So we are building a foundation of computer vision. So in this image, if you want to grab some object from that image, but that image have very low quality lighting conditions, that you may need to enhance the lighting of the that image. If you don't have control over the lighting environment in that while taking the images, the most of the time when you face a bad quality contrast image is when you are dealing with the medical imaging, like the brain MRIs or some X-ray image. In that case, you may face a image which is by naturally taken with the physical cameras that provide very poor quality light intensities. So you need to do enhancing the lighting intensities as your first step toward your image processing pre-processing. So this is the need of the contrast enhancement. If you already know that concepts, so just skip to the further algorithmic point. So before equalizing, let's first understand what a histogram is. Although I have explained in a previous lecture, let's review the concept of histogram and move on to Wikipedia to look what is image histogram. The Wikipedia says an image histogram is a type of histogram that acts as a graphical representation of the tonal distribution of in an digital image. Does it make sense? Doesn't make sense to me. So move on to a histogram. Basically, histogram is a concept in a statistical terms. If you had previously done this in your computer science related or some statistic book, a histogram is an accurate representation of a distribution of numerical data. It is an estimate of probability distribution. This term is very important to remember here, as we are going to use this probability distribution term in our ongoing lecture. And the second one is of continuous variable and was first introduced by Carl Pearson. It differs from a bar graph in a sense that a bar graph relates two variables, but a histogram relates only one. To construct a histogram, the first step is to bin or bucket. So remember this term, the bucket. The range of the values, that is the total values in our condition, the light intensity goes from 0 to 255. So that is our total range, 0 to 255. That is to divide the entire range of the values into a series of intervals and then count how many values fall into each interval. So that make a little sense. Focus on this term once again. To construct a histogram, that we are going to do in our coding. So we will see how to interpret a term, algorithmic term, and convert that line or term or concept into a real coding in an MATLAB. So that is the basic technique that you are going to learn. To construct a histogram, the first step is to bin or bucket the range of the values. So first of all, you need total buckets, buckets of the range, like 255 buckets. You need 255 buckets because you have light intensities ranging from 0 to 255. So you need like a real 255 buckets. And what to do with that bins or buckets? Just divide the entire range of the values into series of intervals and then count how many values fall into each interval. So basically what you are going to do is you are going to calculate the frequency of each light intensity. So basically image histogram is the frequency of the occurrence of a particular intensity value in the total image histogram. Like, let's see an image histogram M hist of I, what it looks like. If we want to see from the image, let's close this and create a separate image. So here we are seeing here in the bottom a gray bar which range from 0 to 255. These are over basically 255 bins. And here we are having in y-axis we are having the number of pixels in that image. So basically 0 to up to the total length of the pixels that this image have. Let's see how many pixels this image really have. To calculate the number of pixels, what we need to do is to find out first the size of this image. So what is the size? The size is simply m by n. And we can calculate the size of the image with the help of size function. So we have m 205 and n 232. So how can we calculate the length? The length is simply m multiplied by n. So we have 4. So what we need to do now, we need to compute all, we need to iterate over all the pixels in that image. So because this is a very big number, we are going to take a smaller example of the image. We will construct our own image with the smaller size like we had done in our previous lecture. In binary image processing, when we convert an image into a binary or find it the connected components, we created our own binary image. We can do that thing again, or we can calculate our image histogram with the smaller size of this over this available image. Like we can just resize this image. The I with the m resize, we can just resize this I with the you can say the 50% resizing, and now you have a size of resized image. Sorry, the resized image size is 103 by 116. Is this a pretty good number? Let's resize it again. This time resize the I 50% time more, and now calculate the size. It's just 52 by 58. That's a pretty good number to do our processing. Let's visualize now the histogram of this image that we just resized. And here you can see now we having the bar ranging from 0 to almost 50 to some value. Okay, so now we have the histogram like this. Here you can see that most of the pixels having the black intensity value. So we want to uniformly distribute these pixel values over entire range of light intensity. So we want to equally distribute or uniformly distribute the light intensity over the whole image. So let's move our code to our editor. I created a file, compute histogram script file, and I loaded a tire image and converted it into 50 by 50 matrix, because this is a two-dimensional matrix of image I. Because the I is a grayscale image, we can just pass the matrix size 50 by 50, and it will resize the I image into a 50 by 50. I stored back this into I variable, so we don't need to create another variable. Here I created a length of bins which is a 256, or -1 will create it to 0 to 255, but in real case it is 256 number, because the 8-bit value can hold up to 0 to 255, mean total 256 values. The second thing is to calculate the size of the image, which is m by n, number of rows multiplied by number of columns. So this is the total pixel length is m by n, and it's stored in the len variable. And finally we displayed our resized image, and if we run this script, we will view a shrinked version of the tire image. So that is our original image that we are going to compute the histogram of. So here I created a function with the name of my histogram. This is also to demonstrate you how to create a function in a MATLAB. To create a function in a MATLAB, you just named to create a script file with the same name of the function, and with the keyword of function, just the returning parameter in my case is a 256 column vector. And second is the name of the function, and in the parenthesis any argument that you want to pass. In my case is the just grayscale image of I. The second thing to calculate the histogram, what I have to do is to first create a list of number of bins L, which is 256, and my hist is the returned parameter that I am going to return to the total histogram that I computed, and I initialized it with the zeros of from 1 to L, mean 256. The second thing is I calculated the size of the provided input image I, and after that I calculated the length, total length, which is m by n. And finally I converted into a one-dimensional matrix, which is a row matrix of my I image to just compute all the histogram in first one for loop. You can use 2 for loops as well by m and n variables, but in my case I am converting the 2-dimensional matrix into 1-dimensional matrix with the help of reshape function. It basically reshape your matrix into any form that you provide. So I provided the second argument is the number of rows, which is in my case is total length of the image, and 1 is the number of columns. In my case this is just 1 because I need 1 column. Finally I iterate over all the one-dimensional image with the help of for loop. I is equal to 1 to len, and my hist is the variable that I created initialized with the zeros, and I indexed it with the help of 1D index provided I and +1, because now I am picking the value, intensity value, which is the intensity value, and adding +1, because the intensity range in I image is 0 to 255, but the MATLAB you don't use 0 indexed, instead it use 1 as first index. So I have to add +1, and I am adding +1 to that in image histogram bin as well. In short, whenever I found a pixel value of a certain light intensity ranging from 0 to 255, I +1 and with the help of that plus 1, which will convert from 1 to 256, I look into the bins, that in my case is my hist, the total bins, and I increment plus 1 to that bin. So that will give me the total frequency of certain intensity value, and in return me the total histogram of the image. So I can use in my compute histogram script, and the total value, basically I shifted it to a separate function. My hist is equal to my histogram, and I will provide I to this function. And finally I can plot the resulting histogram X matrix from 1 to 256, my histogram that I just computed, and second value is to 1 to 256, and the histogram computed with the help of imhist function. So this will just help me to compare the result from both histograms. So here you can see the histogram is identical, mean both histograms are very similar. So this is a basic method to enhance or the equalize the histogram. So what I am using this table from this citation that you can see, Manhans Pratima and Thakral Shavita. Comparative analysis of different wavelet filters and image enhancement using histogram equalization. So this is a table, and the first of all you can see the first value we need to compute is the pixel intensity, and the second value is number of pixels. What are the number of pixels of intensity value 1? Okay, so in their case they showed that it is 1, and what is the intensity value of 2? It is 3. What is the intensity value of 3? It is 3, and 4 2, and 5 2. Okay, so here you can see that this is the value to total number of pixels. It simply means the histogram that we just computed. The next thing we need to compute is the probability of the pixel. So to calculate the probability, you simply need to divide with the total numbers, the number of pixels divided by total pixels, and you know that the final total sum of the probability should be 1. And the next thing that you need to calculate is cumulative density functions, or CDF. To calculate the CDF, what you have to do is just to add up the previous probabilities. So the first will be 0.0625, and the second one will be the addition of the second occurrence and the previous all occurrence. So what you need to do is take the value from the first table and add up the next occurrence, and you will end up with that 0.25, and so on. You can process all these values. And the next thing that you will need to do is to multiply this with total number of pixels intensity, or the bins that you are tackling with, which is the L value. L minus 1 could be the 0 to 255, and in our case it will be CDF multiplied by 255. So you will but in this research paper they are using the 20 in this particular image, and to CD, if they divide the cumulative density function CDF to the total length of L, they will end up with this. And by rounding up the values, the floor rounding to round down, they will get the value of 1, 5, 8, 11, and 13. This is the this is the method to equalize the density or equalize the histogram of the image. So we are going to do all these steps in the MATLAB coding, and you will see how we can do all these steps with the help of MATLAB coding. So let's first create a dummy histogram. So I will call this dummy hist to just visualize what is going on under the hood. So I will create a dummy histogram for just 1, 2, 3, 4, 5 pixel values, and for the reference I am using the same value provided under this table. Okay, so just to compare the results according. So what value they have? 1, 3, 3, 2, 2. So I am going to put these values in MATLAB matrix 1, 3, 3, 2, 2. So now we have our histogram. We can just plot our histogram, although it doesn't make sense, but just to see what we are going. This is not the way to plot the histogram. Instead, we will plot it with the help of stem function. Okay. So with the help of stem function, it will look like this. You can arrange the axis accordingly, but I am leaving this exercise to you. So if we adjust the x and y limits, and we will see the plot like this. Next, we need to compute the total sum of the pixels, and we can simply use the sum function and provide the dum hist variable, and it will give us the result of the total pixel numbers, which is n. In our case, I will hold this 11 to n. The next thing, we need to compute the probability. To calculate the probability, all we have to do is to pick a number and divide by total number. So what we are going to do is to divide all the values with the specified total summation of the pixel values. So this division is our result of the probabilities of all the values. These values are going to differ from the table that we previously shown, because their total number of the total number of L they are going to use is 20, because they have total 20 bins. But in our case, we are going to deal with just the 5 bins of the gray intensities. So these are going to differ. I am going to just demonstrate the concept, and then we will create a function for it, so that we can see all the values from the any number of any size of the image or histogram. So all you have to do is to compute a histogram. In our case, we computed a dummy histogram and divided by the and sum the total numbers like this. Dum hist, the total function will be like this, and sum of dum hist. Okay, so now these are our probabilities. So to calculate the CDFs, we have to add up all the probabilities with the previous number. To do this, first of all, we need to create an empty matrix for this, and in our case, we are going to just initialize it with zeros function 1 to length of dum hist, because all the values will be equal to the original histogram. So the length will be the equal of all the total the histogram, the PDF, and the CDF will be the equal. Next, we need to iterate over PDF values. To iterate, we just need to create a for loop from I to 2 to length of the probes, and after that we need to put the value of I n is equal to I minus 1, because we initialized it with 2, not from the 1, and from minus 1 plus the probability of the I, mean the probability value of second index will be added to the previous CDF value. So before doing this for loop, we also need to initialize the first value of CDF's matrix with the first index with the equal to the probability matrix, the vector of the first value. So we need to equate these equal to 1, and here you are seeing that the final value is 0.9091. So it means our CDF is wrong. We need to recalculate it, which is just because we calculated the CDF before putting any value in the CDF's all one first index. So the first index was 0, but it should be equal to the prop's first value. So now if we try to recompute the value, and we will see that our CDF's all value, the final value, the last value should be 1. If it is 1, it means your CDF value is calculated correctly. If it is not 1, it means there is some error in the calculation. The next thing that we need to do is to sk multiplied by x multiplied by l minus 1 formula, which is just to CDF multiplied by the total length of the bins that we are using, and in our case we are using just the 5 bins, so we need to minus 1 to take it from 1, because if we are using 0 to 255, it means we need to convert 256 number into 255. So to do this, we just need to minus 1. So that's why we are doing here minus 1. Don't forget to add parentheses if you are not previously if you had not previously calculated your L value. So by multiplying CDF's all vector with the length of CDF's all minus 1, you are just computing your sk vector, which is just like this. And now all you have to do is to round up this, because floor this, it will become 0, will become 0, 1 will become 1, 2 will become 2.5 will become 2, 3 will be 3, and 4 will be 4, 4.0 will be 4. So all you have to do is to convert these double numbers into integers. And in MATLAB you can do this with the help of uint8 function. You just pass to the value of the double matrix that you previously calculated, and it will return you the integer value. So you will get the 1 0 1 3 3 3 4. So that is your final round of matrix of your new histogram. All you have to do is to convert these values to your histograms. Now one need to notice is that these answer should be between 0 to total number of your L minus 1, right? The L value, if L value is equal to 256, then this answer should be equal to 0 to 255. So this is also to double check that your answer you are computing the correct value. So what are these values? What these values are? So these values are just the bins. These are the buckets. It means that the new bucket order should be like this. This is your new histogram that you are going to compute. So to calculate the new histogram, all you have to do is to create a new matrix, or new hist is equal to initialize all values with the zeros, so that you don't manually have to add the values of 0 to the empty bins that you don't get from this answer. Here you can see that you did not get the value of 2, right? You did not get a second value, the number 2 in your answer. So at the index of number 2 you have to or at the third bin, in our case in MATLAB, because it is used in 0 plus 1, or at the tooth bin you need to add a 0. So if you initialize all the values with the 0, you don't manually have to put that 0 in it. So this is just an MATLAB specific thing. So initialize it with zeros from the total number of L. In our case, the L is right, the 5. So all we have to do is to create a 5 column vector. So now we have 5 zeros. So we need to map our answer to the new things. So our dummy hist was like this. Now we need again our dummy histogram, right? So here you need to put attention on here like this. The first index is 0, but in MATLAB it is 1. Okay, so don't confuse in it. So consider these just like your 5 bins. Okay, so at the 0th bin you have the pixel value of 1, right? So you got the answer 0 and here is 1. You will get this value from the dummy your original histogram that you are dealing with, and you will put this 1 into your new histogram, right? The second thing, you get the 1, so you have to look on the first bin. This is your first bin. Now here you have the value of 3. Because the first is occurred one time, you need to put this here just 3. The second thing, you don't have any value of 2, so you at the next value you need to remain 0, right? So at the third you occur 2 times number 3. Okay, it means here and here you need to sum up these 2 values, right? So you need to sum up these values. You need to put attention here that these values from your answer are the bin values, okay? But it occurs at a specific index value, which is your value in the image histogram that you provided at the input. Okay, so 1 2 3 4 5, 1 2 3 4 5. So these values should be equal, right? The five values. But the histogram, the value will be picked from here. Now this 3 occurs at 2 times. You need to sum up these 2 values, which is the same index, holding the same index. Okay, so if you sum up 3 and 2, it will end up the 5, and you will put at third place 0 1 2 3. Here you will place the 5, right? The final thing is 4, which is the last value. You will get this 2 and put at the 4th index provided by here. Mean you need to add up 4 plus 1 in case of MATLAB. So now next we will see how we'll do this algorithmically in the MATLAB, or how to implement this via code. So all we have to do is to create a new variable for RF value. This is our resulted float value, which is just the integer version of the SK. Now we need to iterate over these result, which is I is equal to 1 to length of the RF. Now we have to put some value in new histogram with the +1, because over the RF value is -1 value, so we need to +1 here to properly convert the indices in our new histogram. And we because we have initialized it with the zeros, new histogram first was zeros, so if we add 0 to new some value, it will just be the new value, but if it hold the previous value, it will add up to this new value, so it will be sum up. So here you can see the result 13052, because in our RF value we see 3 at 2 times, but we never face the 2, so here we have 2 as 0. The second the second bin 0 1, second bin is 0, and the third bin is 5 because it occurs 2 times. And in our dummy histogram, which we are dealing with, the value is 3 plus 2, which is equal to 5. So that is the total function to equalizing this. So let's create a function of this equalization method and see how it will equalize our image. So here I created a new function of my hist equalization function, and I provided the same name of the variable that we just used in our command window, dum hist and new hist, as a returning variable. First of all, I computed the length and then the new hist variable initialized with the zeros. Next, I calculated the total number of pixels and the probability for the pixels. Next, I computed the CDF by initializing 1 to L and equalizing the first index of probability and CDF with the same value. Next, I iterated a loop from 2 to L and added the previous CDF value to the current probability value, and finally I multiplied it with the L-1 and calculated the integer value. And with this help of integer value, I updated my new histogram with the help of this new hist updation function that you just saw in the command window. Now let's see how it perform on our data that we previously used. And here you can see, if we call this function, it will return the same value that we saw in our command window before, 13052. So that is our new histogram, which is equalized. And now we will see how it perform on our images, like the image histogram equalization function of the MATLAB version. Here you can see I had computed the 3 histogram. The blue one is the original histogram, the red one is computed with the my histogram equalization function, and the green one is calculated using the MATLAB built-in image histogram equalization function. So here you can see the histogram equalization of my function and the MATLAB built-in function are pretty close, but the only difference that we are facing is that at the ranged value from 110 to 256, my value are pretty small, but the histogram level equalized level in the MATLAB provided function is quite high. So it may be that they are using a slightly different version or enhancing it a little further, but that was pretty close to the original equalization. So that was it. The code I used to calculate it, all 3 values are like these. I first created the histogram of the image histogram of the J function. I created the equalized version of I image and created the histogram with the image J, and using this line I just plotted all 3 with the different colors. So that was the all about the image histogram equalization. To make it further enhanced, you need to see one more function, which is try_u, which will extract the upper triangular part, and we will use this to multiply the kth value with the L or CDF value. We will multiply it with the try_u function of the L. So you can see how we will do this. This function will return a matrix like this. You can use this as a once of upper triangular part. You can use this if you are directly dealing with the 2-dimensional image and not using a single histogram. If you are directly dealing with the images directly and convert the image to image enhancement, then you can do this. But if you are doing the histogram to histogram equalization, you can use the code that I had used previously before. Now we will convert that histogram from the we will create an image from this histogram. So the left portion is to retrieve an image from, like we are getting from the hist equalization function that MATLAB provide. It is providing you an image, not an histogram. But my hist equalization function is providing a histogram, taking a histogram, providing a histogram. But the image hist equalization function provided by MATLAB is taking an image and returning an image. But we will calculate an image from the histogram. Now the next part we are going to deal with is to get an image from the histogram. Now, one thing to remember that once we have any histogram, we don't have a method to see where to put those intensities without any context. So we have to keep the context available, which is in our case is the original image. So we need to find out where certain intensity value is occurring in the image. So I had created a new function with the help of this unpublished work of digital image processing, histogram equalization matching file. So the algorithm is very similar that we had created the previous. We first need to L value, which is the 256 or the number of total bins. We can create a size matrix mn, then the length. This is also a similar value. Then with the help of imhist function, we calculated the histogram of the image. So these steps are very similar. Now we need to create the probability by dividing the total length. This step is also the similar with the previous one that we had seen before. Here is the triangular upper part calculation method. Now we had created the CDF and SK with this just simple one equation by multiplying the probability, all probabilities, with this upper triangular part that we had seen before with the help of L value, which is 256 in our case. Now we created a new image. Instead of creating a new histogram, we created the total new image. And but the for loop that we created is just to iterate over the histogram, which is from 0 to L minus 1. So we are seeing using the +1 variable here, k plus 1. We are iterating with the help of k loop matrix. This if statement is just to save some computation, which is to check if the probability is greater than 0. So we are checking if the probability is greater to 0. We are listing out all the indices that hold the intensity value. This is the same to check the intensity value, right? So as I had told you before that we need to calculate the intensities. So we just get these k value, which is 0 to L minus 1. So now what we are doing, we are iterating over original image, and from original image we are visualizing, we are getting all the indices which holds that specific intensity value. So what we need to do is to convert those intensity values with the help of SK matrix. So SK matrix is just this is a CDF value without multiplied by L. So if we get the as L multiplied, if we multiply with the L, we will get the original SK value, which we are doing in our previous histogram equalization method. Like this, we are multiplying it with L. Okay, so we are multiplying it here again, and we are getting this value of L, and now we are putting in the new image matrix all the indices. We get all the indices, we place the all indices, and we just multiplying the total length with the CDF, calculated CDF. So if we just say this SK to CDF, and it will be like this. So so it will be like this, and now we have the same image returned, the image value. So we can check this as well with the help of this function. Inner matrix dimension must agree. To remove that inner dimensional error, we need to just convert this, we need to transpose the probability matrix. It is a row matrix. We need to convert this vector into a column vector instead of a row vector. So after that we calculated these values, and now let's see how it works. And if we do this, and it will show the image. Here you are visualizing a white image instead of a nice looking tire. We are just having experience of a white block. so it will assuming that it will just putting a 1 all over the pixels. So the last thing that we forgot is to round off the values just using the uint8 function. So remember, we need to convert our values into the integer values because they are the double values. So we need to convert the uint8 over new image is equal to uint8 new image. So we need to convert this value into a integer value. So that the new m variable. So let's see if this work or not. And yes, you are visualizing a properly enhanced image. So let's display this image side by side. Figure im show subplot 1 to 1 m show I title original image, and along with this subplot 1 to 2 and m show new m, and put a title of enhanced image. It is also called the image the histogram flattering or the histogram equalization. So now you are seeing the properly equalized histogram. So that is the all for today's. Last thing, if you want to see the new histogram that we just equalized and the provided by image MATLAB image. So here are the two comparative plottings. The blue one is equalized with the help of MATLAB provided function, and the red one is equalized with our equalization technique. So that is all for today's lecture. The next upcoming lecture will be upon more information about the histogram and histogram matching, which is another important topic in grayscale manipulation. So please subscribe the channel if you don't have subscribed already to view future lectures, or if you have any question, just put in the comments. So that's all for today's lecture. See you in the next one. Take care.